Hi everyone, my name is Karen and today I'll be talking about isentropic flow for unit ENG 480. So isentropic flow is an adiabatic and frictionless fluid flow with constant entropy. Adiabatic refers to a system where heat does not enter or leave, and frictionless, no friction, and constant entropy. Entropy is a system's thermal energy that cannot be converted into mechanical work. So that needs to stay constant for an isentropic flow. Now, in this unit, we will be analysing isentropic flow through ducts. So the main duct we'll be dealing with is a converging and diverging duct. So the fluid flows through this way. This is a converging only duct, and you will be dealing with this in your lab. And this is a diverging only duct when fluid goes through this way. So to understand the important variables in isentropic flow, as we were dealing with compressible fluids, we will be dealing with mainly compressible gases. So using the ideal gas law, P equals rho RT, these are the main variables we will be dealing with: pressure, density, gas constant, and temperature. So another important variable we'll be dealing with is Mach number, because fluid flow has a velocity. So Mach number is a dimensionless measure of compressibility in a fluid flow, and it's defined as the ratio of velocity on speed of sound. So ma equals velocity on speed of sound. And because our system does not have constant static temperature, the speed of sound would depend on temperature. So C equals root square root of RTK. You can find this in your book. So with Mach number, if the Mach number equals 1, it is sonic flow. If the Mach number is less than 1, it is subsonic flow. And if Mach number is above 1, it is supersonic flow. Okay, so now we will, when calculating or analysing a duct, it is useful to refer back to stagnation points. So these are, so there is your converging diverging duct, and your stagnation points are here. So these big areas are your stagnation points, and they're used to refer back to because they have zero velocity in there and entropy that corresponds to the entropy of the fluid flow. So in here you would have a variable called T0, P0, and same here, P0, T0. This is your P0, T0, and P01, and P0, T02. Now, because it is a adiabatic flow, meaning that heat does not enter or leave the system, you can assume that T01 equals T02. Now, usually when calculating or analysing ducts like this, it will ask you to find the entry and exit variables, and your entry is here. This portion of the duct, this is your entry. If fluid flowing is this way, this here will be your entry, and this here will be your exit, because you're entering the duct here and exiting to the duct here. So this is where you would find your like P1, T1 and P2, T2. Yep. Okay, so when and where does isentropic flow occur? So isentropic flow occurs when the change in variables is small and gradual in a streamwise direction only. So that's your streamwise direction. What do we talk about now? So to determine whether the flow entering and exiting the duct is either subsonic or supersonic or sonic, it depends on all your variables. So you cannot assume that if flow is going through here subsonically, it would exit supersonically. You need to refer back to your variables and figure it out. So another variable I forgot to mention previously was match number. So you would have a match number, match 1 here, and match 2 here. Yeah. So other variables that you need to take into consideration now, in addition to pressure, density, gas constant, and temperature, is mass flow rate, because we're dealing with flowing gas that has mass. So the other variables is now velocity and area, cross-sectional area, because say this cross-sectional area here will be different to this cross-sectional area here. So now we will talk about a circumstance that happens in a converging and diverging duct, and that is called choked flow. Choked flow occurs when the velocity of the flowing fluid reaches sonic conditions. So choked flow is when velocity equals sonic conditions. And remember, as mentioned previously, sonic conditions is when match equals 1. Now, to determine where it happens in a converging and diverging duct, we look at the equation in the book that states the rate of change of area with the respect to the rate of change in velocity is 0. So this suggests that it happens where the area is either at the maximum or a minimum. So in a converging and diverging duct, it would happen at the throat. This is called a throat. So another way to determine if a choked flow has occurred, we look at pressures. So this is your converging diverging duct. This is your P1 and this is your P2. Choked flow has occurred when the pressure downstream is 52.8% of the pressure upstream. So P2 is equal to 0.5 to 8 P1, and that means choked flow has occurred at the throat, and remember, choked flow is when match equals 1. Okay, what else do I need to talk about? So the thing I got confused with was that I assumed after match equals 1, the velocity of the flowing fluid is constant. This is incorrect, because flowing fluid depends on your mass flow rate, which is density, velocity, area. And as you move along your duct, your area is constantly changing. Therefore, your density is constantly changing. Therefore, your velocity needs to constantly change as well. I think that is all I need to talk about for today. However, it is good to note that isentropic flow doesn't actually occur in real life. It is a perfect system, and systems in real life aren't perfect. This is because there's friction. There's friction in real life, friction in pipes, friction in ducts. We do use isentropic flow, however, to analyze other flows, such as Rayleigh flow and Fano flow. It's just a good way to not really compare, but a good way to analyze. It assists in the analysis of it. Thank you for listening.